Welcome back. In this session, we are going to discuss quadrature phase shift keying. We are going to discuss the time domain representation in both mathematical form and graphical form for quadrature phase shift keying modulation technique. And also, we are going to plot and analyze the signal constellation plot for quadrature phase shift keying. Quadrature phase shift keying is a digital modulation scheme which modulates the die bits of the incoming binary data the quadrature phase shift keying is a digital modulation technique in which the phase of the sinusoidal carrier is varied in accordance with the binary die bit data. As we already know that the phase angle is having the ranges from 0 to 2 pi. In binary phase shift keying, we are having only two symbols, 1 or 0. So, the entire phase angle can be split into two, that is 0 and pi. And the 0 degree phase angle is used to represent 1, and the binary data 0 is represented by a phase shift of 180 degree in the sinusoidal carrier. But in the case of quadrature phase shift keying, if suppose the incoming binary sequence to a QPSK transmitter is in such a way that 10110 10101, then in BPSK, each bit is represented by a phase shift, 0 degree. This is represented by phase variations, and 0, the next symbol is represented by 0 degree. But in the case of QPSK, we are going to pair two bits, each and every 2 bits in the binary sequence, and this collection of 2 bits is called as die bit. Hence, as we are having 2 binary digits, there are 4 different possible symbols are available: 0, 0, 0, 1, 1, 0, 1, 1. So we are having 4 distinct symbols. Hence, the modulator has to produce any one of the symbol from the symbol set, S1 of t, S2 of t, S3 of t, and S4 of t for the corresponding binary die bit data. And the phase angle deviation given for each of these symbols can be regarded as, we can choose 0 degree. So the entire 360 degree is divided by 4 here. So we can have 90 degree. So there are several different choices are available. One of the choices 0 degree, 90 degree, 270 degree, 180 degree, and 270 degree. This is a kind of choice we can choose to give the phase angle variations for the corresponding symbols. On the other hand, we can choose in a different way that 45 degree, 135 degree, 225 degree, and 315 degree, and each of which are separated by 90 degree. Hence, the phase angle of a sinusoidal carrier is going to be varied with pi by 4, that is in pi by 4 radians, or in terms of degree we can say that 45 degree. Similarly, 3 pi by 4 radians or 135 degree, 5 pi by 4 radians, that is 215 degree, 7 pi by 4 radians, which is represented by 225 degree, and this is 315 degree. And each of which are separated by 90 degree apart, we are having 4 separations and 4 phase angles. Hence, this modulation is called as quadrature phase shift keying or quadri phase shift keying. In general, we can represent all these 4 phase angles with an expression 2i minus 1 pi by 4, where I is equal to 1, 2, 3, and 4. If I is equal to 1, 2i minus 1 will become 1. So pi by 4 will come. If I is equal to 2, 2i minus 1 will become 3. So it represents 3 pi by 4. So if I is equal to 3, 2i minus 1 is 5. So it represents 5 pi by 4. If I is equal to 4, 2i minus 1 is 7. So it represents 7 pi by 4. We know that the carrier signal is chosen as a sinusoidal signal in order to accommodate it with the restricted bandwidth. Hence, the QPSK modulated waveform is given by Si of t is equal to square root of 2Es over Ts cos 2 pi fct minus theta I, and where t is between 0 to Ts. Here, Es is the symbol rate and Ts is the symbol duration. For example, if you choose a binary sequence like this, then one particular bit is represented by the term bit, and the time duration that is occupied by one bit is called as bit duration TB. But in the case of QPSK, we are considering 2 bits as one symbol. So, here, for one symbol, the bit time duration is TB. For 2 symbols, the time duration is TS, that is symbol duration. And here it is referred that the bit duration considered for BPSK is twice the bit duration used for QPSK. So the symbol period represented in QPSK is equal to the bit duration represented in BPSK. Hence, in the same time period, 2 bits are transmitted, so that the data rate will be twice the data rate of the BPSK system. Similarly, every bit is having a bit energy EB, and here each symbol is constructed by 2 bits. So the energy per symbol is equal to twice the bit energy. Here EB is the bit energy. And FC is the carrier frequency. And this equation is in the form of cos A minus B. So we know that cos A minus B can be written as cos A cos B plus sin A sin B. So we can expand this expression cos 2 pi FCT minus 2i minus 1 pi by 4 can be written as cos of 2i minus 1 pi by 4 cos 2 pi FCT plus square root of 2 ES by TS sine of 2i minus 1 pi by 4 into sine 2 pi FCT. So here we can say that I is equal to 1, 2, 3, 4 since each of the value I is representing a particular symbol. So we are having 4 symbols S1 of t, S2 of t, S3 of t and S4 of t, which are all representing the die bits 1, 1, 0, 1, 0, 0 and 1, 0. The S1 of t is used to represent the binary die bit data 1, 1 and S2 of t is used to represent the die bit 0, 1 and S3 of t is used to represent the die bit data 0, 0 and S4 of t is used to represent the die bit data 1, 0. And here we have used the gray encoded die bit data for representing the series of symbols S1 of t, S2 of t, S3 of t and S4 of t. And the reason will be discussed under the signal constellation mapping. Now let us substitute the values I from 1 to 4. So if I is equal to 1, S1 of t is equal to square root of 2 ES by TS. If I is equal to 1, this will become pi by 4 and cos pi by 4 sin pi by 4 will become 1 divided by square root of 2. Hence we can write square root of ES by 2 multiplied by 2 by TS into cos 2 pi FCT plus square root of ES by 2 multiplied by square root of 2 by TS sine 2 pi FCT. That means these two values will become 1 divided by square root of 2. And we are having square root of ES, so we are taking the square root of ES as common along with 1 divided by square root of 2. Hence, the equation can be written like this. Similarly, we can substitute the different values of I. Let us choose the I as 2. Here, cos 3 pi by 4 and sin 3 pi by 4. In the second quadrant, cos 3 pi by 4 is having the negative value and sin 3 pi by 4 is having the positive value. As you know that for pi by 4, all the trigonometric functions are positive, and in 3 pi by 4, in second quadrant, sin is having the only pi by 4, and in the third quadrant, both cos and sine are having the negative values, and in the fourth quadrant sine is having the negative value and cos is having the positive value. Hence, in the third quadrant, cos 3 pi by 4 is having a negative value of negative minus 1 by root 2, and sine will have the positive value, so plus square root of es by 2. Similarly, in the third quadrant, for I is equal to 3, cos pi by 4 and sin pi by 4 both are having negative values. And in the fourth quadrant, there is 7 pi by 4, cos is having the positive value and sin is having the negative value. Now we are having 4 different symbols. If we look at all these 4 symbols, we can find 2 functions that are all having equal and opposite magnitudes. Equal in magnitude but opposite in phase with each other. Moreover, these 2 terms are having a separation of 90 degree in phase angle. That is cos 2 pi fct and sin 2 pi fct are having a phase deviation of 90 degree. Hence, these 4 symbols, that is, here we are having 4 symbols, that is number of symbols m is equal to 4, then the number of dimensions required to represent this 4 symbols, these 4 symbols in the signal space is 2. Always n should be less than m. So we can consider 2 orthonormal basis functions from these 4 set of symbols. Let square root of 2 pi ts cos 2 pi fct as the first orthonormal basis function phi 1 of t, and the square root of 2 pi ts sin 2 pi fct as the second orthonormal basis function phi 2 of t. Hence, the 4 symbols can be represented by S1 of t is equal to plus square root of Es by 2 phi 1 of t plus square root of Es by 2 phi 2 of t. Similarly, further S2 of t is represented by phi 2 of t, the combination of phi 1 of t and phi 2 of t. All S1, S2, S3 and S4 all are written with respect to phi 1 of t and phi 2 of t. If we represent these equations in the matrix form in such a way that S1 of t, S2 of t, S3 of t and S4 of t, which is equal to and this is nothing but the correlation between Si of t and phi j of t. Sij, each of this matrix can be represented as S11, S12, S21, S22, S31, S32, S41, and S42. And Sij is the correlation between Fi of t and phi j of t, where I varies from 1 to 4 and j varies from 1 to 2. And here, this S11, S12 will be considered as the message point S1. S21 and S2 is considered as the message point S2. And S31, S32 are considered as the message point S3. And S41 and S42 are considered as the message point S4. In time domain, the QPSK is represented in graphical form in this way. In each of the die bit represented in the binary sequence given here 0, 1, 1, 0, 1, 0, 0, 0, all these will be odd numbered sequence. That is this position 1, 3, 5, and 7. Similarly, all the even number positions 2, 4, 6, and 8 are represented by Si1 phi1 of t and Si2 phi2 of t correspondingly. And S of t can be written as Si1 phi1 of t plus Si2 phi2 of t. So this S of t can have different values. That is, for 0, 1, then it denotes S2 of t. For 1, 0, it is representing S4 of t. 1, 0 represents S4 of t. For 0, 0, it represents S3 of t. And the phase variations are represented correspondingly. Hence, the signal space of QPSK in two-dimensional n is equal to 2. We have two orthonormal basis functions. So the signal constellation consists of 4 message points as already discussed as S1, S2, S3, and S4. And the coordinates of these message points in the signal space can be represented by the correlation between the symbol and the orthonormal basis function. So Smn can be represented as the integral of Sm of t multiplied with phi n of t over the interval tb, where m varies from 1 to 4 and n varies from 1 to 2. Let us find the message point S1, which is constituted by the x-axis coordinate S11 and which intersects with the y-axis coordinate S12. This is the x-axis coordinate point, this is y-axis coordinate point, and which are all intersecting. And in the xy graph, Cartesian graph, we will have a particular location which is represented by a coordinate which is called as the message point S1. So S11 is nothing but integral over 0 to tb S1 of t phi 1 of t dt, and we know that S1 of t can be written as square root of Es by 2 phi 1 of t plus square root of Es by 2 phi 2 of t. And as we are having two orthonormal basis function, these two orthonormal basis functions are orthogonal to each other. Phi1 of t and phi2 of t are orthogonal to each other. And phi1 of t and phi2 of t are having unit energy. These are all the conditions for the function to be an orthonormal one. Hence, if phi1 of t and phi2 of t are orthogonal to each other, then integral of phi1 of t, phi2 of t dt will become 0, and integral of phi1 of t, that is the energy of this, will be 1, and the energy of phi2 of t will also be equal to 1 joules. This is saying that unit energy constraint, and this is orthogonal constraint. Hence, we can substitute the expression of S1 of t in this location, and it can be written as square root of Es by 2 integral over Tb phi1 square of t dt plus square root of Es by 2 integral of phi1 of t multiplied with phi2 of t dt, and this will become 0. Hence, phi1 of t and phi2 of t are orthogonal to each other, and this will become the energy of the orthonormal basis function phi1 of t, whose value is unit joules. So S11 is square root of Es by 2. Similarly, if we calculate S12, which is representing plus square root of Es by 2, which we have already described here. S11 is equal to plus square root of Es by 2 by comparing these two. Similarly, S12 is represented by plus square root of Es by 2. By this way, we can represent all the message vectors and all the message points in the signal constellation graph, which can be represented by, if I is equal to 1, then the transmitted symbol is S1 of t, and it is having the message point S1. For I is equal to 2, it is S2 of t. For I is equal to 3, it is S3 of t. And for I is equal to 4, it is S4 of t. And for I is equal to 2, the corresponding message point is S2. This is S3 and this is S4. And these two values are the coordinates of the message point, which is corresponding, that is the relationship of Si of t and phi1 of t. Similarly, this is the correlation between Si of t and phi2 of t. So this represents S11, S12, this represents S21, S22, here S31 and S32, this represents S41 and S42, which is having the symbol energies on each of the tabular columns and corresponding rows. And the corresponding gray encoded binary bit data, which is represented over a particular time period of symbol period Ts, representing 11 for the symbol S1 of t, and S2 of t is used to represent 01, and S3 of t is used to represent 00, and S4 of t is used to represent 10. Let us plot all these coordinates in signal constellation map which is having an x-axis, y-axis, which is represented in a Cartesian graph, in which x-axis represents phi 1 of t and y-axis represent phi 2 of t. Now let us start with the message point S1. So in x-axis it is coordinating plus square root of es by 2, and in y-axis it is coordinating plus square root of es by 2. So this is the point square root of es by 2. This is the point in y-axis having a magnitude square root of es by 2. So both this point is representing the coordinate square root of es by 2 comma square root of es by 2. That is S11 comma S21, which is corresponding to the binary data 11. And the next message point S2, in x-axis it is having minus square root of es by 2, and in y-axis it is having plus square root of es by 2. Hence, it is represented at minus square root of es by 2 and intersecting with the y-axis value square root of es by 2, which is representing the coordinates like this. That is S121 and S22. Correspondingly, S3, message point S3 is represented by minus square root of es by 2 minus square root of es by 2, representing S31 and S32. And finally, the message point S4 is represented by square root of es by 2 and minus square root of es by 2, which is representing S41 and S42. This is the way the signal points are represented in the signal constellation graph. Now, this message point represents S11, and this represents S2 represents 01, S3 represents 00, and S4 represents 10. This gray encoded binary data are representing this rotation is done because we can see there is only one bit change in when we rotate go from one coordinate to another coordinate. If the presence of the additive white Gaussian noise relocates the message point at the receiver side to the nearest quadrant, then the corresponding error occur on the die bit is only one bit. That is, single bit error will occur. That is why we are representing the gray code encoded binary data for each of the adjacent coordinates. And moreover, from the origin, if we draw a straight line to that particular message point, it represents the corresponding phase angle. That is, the message point S1 corresponding to the symbol S1 of t is having a phase variation of pi by 4 with respect to the sinusoidal carrier waveform. Hence, here it will be pi by 4 radians. And for message point 2, it is 3 pi by 4. And for message point 3, it is having an angle of 5 pi by 4, and correspondingly for the message point 4, it is having a phase variation from the sinusoidal carrier is 7 pi by 4 radians. And now the distance between each of the message point is called as Euclidean distance. This is D12, this is D14, and this is D34, and this one is D23. The distance between this point is square root distance will be square root of ES by 2 plus square root of ES by 2, which is nothing but 2 into square root of ES by 2, which is equal to square root of 2 ES. And the constellation points are located in such a way that D14 is equal to D12 is equal to D23, which is equal to D34, which are all equal to square root of 2 into ES. And this is a very minimum when considering the hypotenuse, which represents the Euclidean distance between S13 and S24, which representing D24. And this distance is the hypotenuse of this right angle triangle. Let me assume this as a right angle triangle, and this portion will be the hypotenuse, which is nothing but square root of ES by 2 plus ES by 2, that is square root of ES, and here also we will have square root of ES. So D24 and D13 are having the value 2 multiplied by square root of ES. Hence, the adjacent coordinates of the signal constellations are nearly located, whereas the constellation message points, which are all opposite quadrants, are located far away. That is why, even though if the noise is very high, there is a very less probable for having an error in both the bits. And the decision boundary is for deducting the QPSK signal is, here we have to compare the threshold with both the values. So here for x-axis it spreads from, the x-axis is varying from, that is phi1 of t may vary from, or otherwise in the case received signal, the case of received signal, let R be Si plus n, and Si consists of Sij plus n, sorry, Si1 plus n plus Si2 plus n. So there may be a possibility of existing, that is between minus square root of Es by 2 to plus square root of Es by 2 in the x-axis, as well as in the y-axis also. This is can spread from on this area. So we can have the threshold on the x-axis lambda 1 as square root of Es, that is average value, square root of Es by 2, which is equal to 0. Similarly, lambda 2, considering the threshold for y-axis, both are 0. So 0, 0 will be considered as the threshold. So it is considering that x is equal to 0 and y is equal to 0. Both are considered as the decision boundary. So if the x-axis and y-axis are representing the positive values, then it is represented by region Z1, considering that it is the message point S1. It is if the message points are located in the second quadrant, that is in region Z2, where x is less than 0, y is greater than 0, then that will be considered as the message point S2. Similarly, the message point S3 is having the region Z3 on the third quadrant, and the fourth quadrant is for representing the message point S4 in the receiver side, and it is determined by Z4.